Last video, we turned red bauxite into fine white powder. That powder is pure alumina. But powder is not aluminum. To unlock the metal inside, we need something far more powerful. Electricity. The method that changed the world is called the Hall-Héroult process. It's the foundation of the modern aluminum industry. However, alumina cannot be electrolyzed directly. Its melting point is extremely high, above 2000 degrees Celsius. So we must find a way to lower its melting point before electrolysis can begin. Let's see how engineers solve this challenge. First, we need an electrolytic cell with a metal shell. Inside the cell is a graphitized cathode lining. Above it are carbon block anodes. The cell is covered with a lid that contains a feeding port. And at the bottom, a vacuum ladle is used to collect molten aluminum. Now we add solid or granular cryolite into the cell. When electricity is applied, the cryolite is heated to about 950 to 1000 degrees Celsius. It melts into a liquid and becomes the electrolyte. Then alumina is added into the cell. Now the electrolysis can begin. Aluminum ions gain electrons at the cathode and form aluminum metal. Oxygen ions lose electrons at the anode and form gas. Molten aluminum gradually collects at the bottom of the cell. Using the vacuum ladle, the molten aluminum is siphoned out. And this is how we obtain liquid aluminum. The overall chemical reaction can be written as follows. One important detail: during electrolysis, the carbon anodes are slowly consumed, so they must be replaced regularly. Now, let's see how the Hall-Héroult process works inside a real factory. Some viewers may already recognize what this scene shows. That's right, this is the process of preparing the electrolyte. Those white granules are the cryolite we mentioned earlier. Once the electrolyte is ready, the electrolysis of alumina can begin. The process requires continuous heating. The temperature inside the electrolytic cell must be kept between 950 and 1000 degrees Celsius. Look closely. Those dark objects hanging above the cell are carbon anodes. They are essentially graphite carbon blocks made mainly from petroleum coke and coal tar pitch. During electrolysis, these carbon anodes are gradually consumed. Producing 1 ton of aluminum typically consumes about 430 to 500 kilograms of carbon anodes. That's why they must be replaced regularly. Once enough molten aluminum has collected at the bottom of the cell, it can be extracted using a vacuum ladle. Nowadays, almost all primary aluminum in the world is produced using this method, from white alumina powder to shining liquid metal. This is the final step that makes aluminum possible. Follow us. We'll take you through the whole life of bauxite. In the next video, we'll show the magic of aluminum alloys.